Let's get started here. So test number 2 is next time. We'll spend part of our class today reviewing for the exam. Project number 4 was emailed back to all of you. As I indicated on my message board posting, or listserv posting, everything was pretty good with the projects. There were just 3 small comments I wanted to make. First of all, please make sure that you always actually state the hypotheses for whatever you're testing. So, for example, I always want to see something like this when you are actually performing a hypothesis test. So I always want to see something like that. Also, please make sure to use the correct notation. I had a number of students do something like this to indicate x squared. It's not that difficult to type in x and then use the superscript button and put a 2 up there. It's not that difficult. Okay? And lastly, when you're using CP, please make sure that you're comparing it to P, not P minus 1. A number of you were comparing it to the number of predictor variables that were in the model. You should be comparing CP to P itself. Okay, and and just because if you say, well, one model's better than the other one because the CP is lower, that's not necessarily correct. Again, you're comparing it to P, not necessarily which one is lower, like what you would have, for example, with AIC. Okay, so I just wanted to clarify that. Were there any questions about the project? Okay, are there any questions overall before we get started today? Okay, note that project number 5, it's already written, but you need to basically have been through all of chapter 10 first before you can start it. So I plan on handing it out on Tuesday, November 20th, or posted to the web on Tuesday, November 20th. And it will be due the Friday before Dead Week. And like I said, it's going to be a shorter project. It's about half the length of a normal project, since obviously we're getting towards the end of the semester. But I think it would be useful for you to have the experience of that project before you take the final. Okay, if there's no questions then, let's take a look at where we left off in the notes, which was page 1013. So last time I introduced 2 measures that allow us to try to find outliers. One of these measures was called a studentized residual, and it was denoted by R sub I. Simply, it's the residual divided by its square root of its estimated variance. And this R sub I has a t-distribution with n minus p degrees of freedom. We also looked at a studentized deleted residual as well, and that was denoted by t sub I, and this had a t-distribution with n minus p minus 1 degrees of freedom. Because we have these t-distributions, that allows us to get a probable range for where you would expect most of these types of residuals to fall within. So, for example, with a studentized residual, we would look to see if all of them are between the negative 1 minus alpha divided by 2 quantile from a t-distribution, and as an upper bound, just the 1 minus alpha divided by 2 quantile from that corresponding t-distribution. If you have a value, a studentized residual within there that says, okay, it's okay. It's It's not an outlier. If you have something outside there, then you're going to start worrying if maybe the model's not fitting that particular observation well. Now, just because it's outside that range doesn't mean, though, it is a problem. For example, we know that if alpha was 0.01 and we had 100 observations, how many observations on average would you expect to be outside that range? Well, 0.01 times 100, 1. Okay? Now, if you start having, let's say, 10 observations outside that range, then you're starting to worry, because it would be quite unusual for that to happen if everything was okay with your model. Also, if you do have just, let's say, one observation outside that range, and let's say it's really, really far outside that range, again, that's another case for you to start worrying. And maybe there's a problem with the model for that observation. So that's how you would work with the studentized residuals. Studentized deleted residuals, basically the same concept. Now you just have the different degrees of freedom. Okay, so let's actually look at a numerical example with these types of residuals. To find a studentized residual in R, you can use the R standard function. To find the studentized deleted residual, use the R student function. Note that this can be a little bit confusing if you're not necessarily totally paying attention to what these functions are doing. For example, note that, hold on, I want to make sure I got the notation here right. Just give me a second. Yeah, I did. Okay. So this R student here, notice it has R in front of it. And so you might be thinking, oh, okay, we're talking about the studentized residual, since you have R student. But no, that's not correct. Instead, we're talking about the studentized deleted residual. And perhaps this is what caused me to pause there for a second. Notice how I have a T sub I here in the middle? Well, then I would need a -1 also there as well. Sorry about that. So R standard goes with the studentized residuals. R student goes with the studentized deleted residuals. Okay. So we've already, let's say, estimated our model with the NBA guard data set that has the 4 variables remaining, based upon our Chapter 9 findings. We have the results, let's say, stored in an object called mod.fit. And then we just simply use the R standard, R student functions. Notice the argument name is simply called model. So you say model equal mod.fit. And you get the corresponding values out. So for example, for the first observation, here is R1. Here is T1. Are those outliers? Is the first observation outlier? Yes or no? No. These, we would get our values from our T distribution, and in fact, if you look down here a little bit, if I use alpha 0.01 for the studentized residuals, and for the studentized deleted residuals, we're basically looking within plus or minus 2.625. If it's inside there, great. If it's outside there, then you might start worrying if that's a problem, that observation would be a problem. And we see we don't have a problem there. Now, overall, we have 105 different observations. So while we could simply, print off every observation and look to see, just using our eyes, look to see, if, this type of residuals outside the boundary or not, and that can be kind of a pain, especially even if you have more observations than just 105. So let's look at ways and then we can just have R print off the particular observations that are outside that range. So what we can do is this. We could take the absolute value of the studentized residuals and compare it to, meaning is it greater than a corresponding quantile from the T distribution. Notice I'm doing the absolute value here, so I don't have to worry about an upper bound and a lower bound for the T distribution. And so if I execute just the code that's highlighted there, what's R going to do? Yeah, it's going to give us a whole bunch of falses and trues, and this is what we get. So it does a logical comparison. You know, there are 105 different studentized residuals in there, and it's checking if each are, the absolute value of each are greater than 2.6. And what we see here, we come here some truths. So let's see, observation 52, observation 37, and should be one more, observation 72. Those are the ones that are outside that range. So if we use these truths and falses then, now with R sub I itself, with the brackets there, it tells R which values to return. It's going to return the true ones and not return the false ones. So let's go ahead and do that. And there's 37, 52, and 72. Okay? But notice here, that's not necessarily too far outside this range that we have set. And in fact, we have 105 observations here, so we would expect, we're using alpha 0.01, we would expect about 1 on average to be outside this range. We have 3. Well, that's not too different from 1. So just from looking at this, am I really worried at all? Not in particular. Not really. I'm still going to look back to my data set and examine those particular observations, because if they have something in common in terms of, let's say, their predicted variable values, that might tell us that maybe the model is having problems fitting those kinds of, in this case, NBA guards. We'll do that later in Chapter 10 when we refine our model in more detail. Right now we're just looking at some of these measures to detect possible problems. We can also do the same thing now with the studentized deleted residual as well. And now we also have observation 53 that pops up. But notice it's just barely over the boundary line. Now again, there's a lot of observations that you would need to look through to find when are you outside these boundaries or not. And so because of that, in addition to doing something like this, people usually plot these types of residuals. So the plot, we'll take a look at the plot first here. This is the plot on page 1016. On the y-axis, I plot the studentized residuals. So these are the R sub I values. And on the x-axis, I put the estimated mean response. In other words, y hat. The boundary lines then are drawn at t-distribution value of 0.995 with n minus p degrees of freedom. This would be the negative version of that. Okay. Then the darker red lines correspond to Bonferroni corrected values. If you remember us talking about this last time. So this would be t of 1 minus alpha, I think I used 0.05, t minus 0.05 divided by 2 times n, and n minus p degrees of freedom. And down here we just have the negative version of it. Okay? So we see that, yes, these observations that we had identified before, 52, 37, and 72, are just a little bit above that boundary line. But notice it's still within that Bonferroni corrected area. So, I'm not as worried because of that. Again, if it was outside that area, then I would be, again, more worried about my model. So let's talk about how this plot is actually done. So I plot my y-hat values on the x-axis. I plot the studentized residuals on the y-axis. I'll let you look at this on your own. I control the y-axis limits in a way to make sure that all observations are listed there, and also those horizontal lines are listed there as well. So please take a look at my code for how I do that. And so if I just do this part right here, you can see my initial plot. And then I do a horizontal line at 0. Remember, residuals themselves are centered at 0. And then for my first set of boundary lines, I just get the corresponding quantiles from my t-distribution, a negative version and a positive version of the same thing, and I draw them out. I do the same thing for the Bonferroni corrected ones. And lastly, I use, if you remember, the identify function that we've used before. I use the identify function to interactively identify the corresponding observation by simply clicking on the plot. And so there's my plot. Are there any questions? Let's go on to page 1017 then. You can also see the plot of the studentized deleted residuals as well. Notice how, again, observation 53 now is above that one of those boundary lines. Now, in the CAR package, there happens to be a function called Outlier Test, which actually gives you a formal hypothesis test of, are there outliers? In other words, all it's going to do is check. With respect to the studentized residuals, or let me make sure I got that right. With respect to the studentized deleted residuals, it's going to check, are there any observations above that dark red line or below the dark red line. That's all it's doing. But it's doing it in a more of a formal hypothesis test manner. So to actually use the function called Outlier Test, just say model equal mod.fit. And what it's going to do is find the largest and absolute value studentized residual, studentized deleted residual. Notice how it says R student here. Remember how the R student function finds the studentized deleted residuals. And it does what's first of all called an unadjusted p-value. What does that mean? Well, remember we have a particular range that we would expect these values, these studentized deleted values to fall within. So all it's doing is this, just calculate a regular old p-value, like for like a t-test. 2 times the probability that, let's say, a random variable A is greater than, in this case, R37, where A is distributed t-distribution with n minus p minus 1 degrees of freedom. That's all it's doing. And it gets a probability of, or 2 times the probability of 0.001. Notice it's kind of small, but that's why you see it above the lighter red line. Now, when we use a Bonferroni correction, because remember, essentially what we're doing is looking at 105 observations, so it's like doing 105 different hypothesis tests. Then it takes simply this p-value times 105. We've looked at Bonferroni corrected p-values before, same concept. So 10 times 0.001 is 0.1 about. And so if I use alpha 0.05 as a criteria, don't reject. Notice that this 0.05 here is the default. If you wanted to use something else, there is an argument in here called cutoff, and you can specify a different value if needed. I also go through the process of then showing in R how to find then these corresponding p-values, which should not necessarily be a surprise how I did that. Okay. Just some final notes. I've already said 1 before. We've already basically said 2. Number 3 here, just be careful if you look at the help for this particular function. It says it's using studentized residuals. It is actually using studentized deleted residuals. So if you actually look at the function, and we just kind of confirmed it too, we're doing some additional calculations. it is actually using studentized lead residual, so the help is actually wrong for it, which is not very helpful. Are there any questions? Okay. We're going to start talking about the hat matrix some more. And with the hat matrix, the thing that's most important usually is the diagonal elements of it, the h sub I. So h11 is for the diagonal element, the 1, 1 diagonal element, for example. And well, I haven't said this before. Basically, what these diagonal elements kind of represent is a measurement of the distance of the ith observation to the mean of all the x observations. Kind of a measurement of distance. Okay? The larger the value, the farther it away is from the mean. The lowest possible value for HII is actually 0. So the farther away from 0, the positive direction means the farther the observation is from the, let's say, the center of all your x, all your predictor variable values. So let's take a look at a quick example that illustrates that. So this is the advertisement responses data that we first saw in Chapter 6. And if you remember, we use size and circulation to try to predict the number of ad responses. In this particular setting, to get the HII values, I can use a function called hat values. Not too difficult. So here's just, I enter in the data, I use the LM function to estimate the model, and then I pull out the hat matrix diagonal values using hat values. Here's a plot of the data. Now on the x-axis, I have one of the predictive variables. On the y-axis, I have the other predictive variable. Notice I do not have the response variable at all. So it's just a scatter plot of, let's say, x1 versus x2. And what I decided to do was find the mean of all the circulations, so it was right about here. Find the mean of all the size values, right about here. And if you join these up, you get the overall mean then of the x's. Okay? Now the circular points represent the actual observations. Right above each of the circular points, I plot what the hat matrix diagonal value was for that particular observation. So for example, observation number 5 had a circulation of 40,000, a size of 6, hat matrix diagonal value 0.226. Notice how that point is the one that's the closest to the overall mean, and also has the smallest hat matrix diagonal value. And as we get farther away from the mean, these hat matrix diagonal values tend to increase. Now, you do have to be a little bit careful, though, because this plot can be a little bit misleading. And that is, notice these two predictor variables are measured on different scales. So, if you're just simply looking at the distance from here to here and thinking, well, geez, that looks just to be the same as the distance from there to there, but they're different values. Well, you had to put it into the context of the scales that we're measuring these variables. So it's a little bit misleading, but it's a nice little introduction for you to see what hat matrix diagonal values look like graphically. Okay, some properties of the hat matrix diagonal values. They are always greater than 0, and they are always less than 1. The closer to 1 a hat matrix diagonal value is, the farther the observation is from the, let's say, the center of all your observations. So let's think about what this means in the context of what we're doing here. If I have an observation that's close to the center, or no, let's think about this one. If I have an observation that's farther away, then what that says is it's farther away from the most of the information that you know about your data or about your sample. And so because of that, you might be concerned that since that observation is so far away, it might exert a particular kind of, let's say, influence more so than the ones that are in the middle, which are in the center of the data. And you'll see how that occurs shortly. So, hat matrix diagonal values between 0 and 1. The sum of all these hat matrix diagonal values happens to be P. And in fact, if you were to add all these values up, you would get 3. 2 predictor variables, then they intersect. This HII is often called a leverage. The leverage of the ith observation. If we think about what the word leverage means in a non-statistical context, you can think of if one person has, let's say, leverage over another person, maybe that they have a way to exert their influence over another. And that's how this HII helps us then determine in a statistical context maybe particular observations that have an influence on what the B's end up being, what the corresponding Y hats end up being. So the closer to 1 the HII is, the more important that Y sub I then is to determine its corresponding Y hat sub I. Again, think of influence here. Why is that? Why did I say this here? Well, again, remember, the hat matrix basically puts the hat on Y. So it's H times Y. And if you look at, let's say, for example, your first observation, say Y1, and you want to estimate it, notice what this means, that H times Y. It means you have B0 plus, it means that you have this. How do I want to write this? H11 times Y1 plus H12 times Y2 plus all the way down to H1n times Yn. So notice that the larger the H11 is, the more influence that particular observation then has on determining its corresponding predicted value. Think about how that might, let's say, bias, you could say, your results. If one observation is having a large say-so in what its corresponding predicted value is, then you might be worried that, well, maybe this model is not necessarily good. That just this one observation is having a large influence on what its predicted value is. Take a look at this. Look where HII ends up being in our studentized residual and studentized leader residual equations. So if H sub II is large, meaning it's close to 1, what's going to happen to the denominator? It's going to go down because we have that 1 minus HII there, meaning that 1 minus a large number close to 1 is going to be close to 0. And then if the denominator is small, what's going to happen then to R sub I and T sub I? Go up. So you can see how that hat matrix diagonal value can cause you to have large studentized residuals and studentized leader residuals. Number 6. What you're going to see is that observations that have a large HII can tend to pull the regression line towards the corresponding observed value of Y. And this can then cause your residual to be small. So normally we think, well, a small residual means, okay, that observation is being fit well by the model. Well, yeah, it might be fit well, but maybe too well. That this one observation might be really influencing the model's fit. And I guess also to put this into another context, think about what would happen if you do have an observation that has high influence. Suppose that observation wasn't observed in your data. Then what that means is that your model could change a lot. And we don't want our model to change a lot just by one observation being in the data set or not being in the data set. Well, what is a large HII value? Well, there's not necessarily agreement on what would be large. Here are two criteria that are often used. If h sub I is greater than 2 times p divided by n, or if HII is greater than 0.5, you have very high leverage. It's between 0.2 and 0.5, you have moderate leverage. And these rules, or these rules of thumb, apply when the sample size is large. Now, large HII values are not necessarily bad, and this kind of corresponds to a discussion that we had last time. If I...
You will always have large, some large.
Well, first of all, it depends upon what you mean by large. You will not necessarily always have this occurring if you call that large. You'll see examples when we actually do some data, work with some data. But typically speaking, imagine a data set where you didn't have this observation, didn't have that observation. If we estimate a regression line or regression model, obviously it's going to go through those points. Then if we did have that particular observation, notice how that's kind of far from the center of all the x's. In this case, we only have one predictor variable. So the center of the axis is right about here. And relatively speaking, compared to all the other observations, it is kind of far. So it's going to have a larger HII compared to the other ones. But it's not necessarily detrimental to your model because it continues the same association. If instead of this observation, suppose we had this particular observation, again, that's going to have a large HII because it is far from the center of the x's. But in this case, what's going to happen is the model is going to start looking something like that, where it's going to basically exert influence to push down that regression model, having leverage on it. It's going to push it down towards it. And we don't want that to happen because that totally changes our understanding of our model. Okay, let's take a look at an example. So this is with the high school and college GPA data set again. I think this is a good example. We had 20 observations, but let's say that we added 25th. We had a student who did very, very well in high school, took the advanced placement classes, got a GPA of 4.35. Then when they went to college, they decided to party all the time. And their college GPA, not good, 1.5. Well, what happens to our model if this observation is added? So first of all, how do you add the observation to the data set? Just to make sure this is clear, I read in my original data, and then I use the rbind function, which I believe we've seen before, which says combine by row. So I'm going to take my original GPA data set, and now I'm going to put my new observation right below it. So I have a new data frame listed there. That's what rbind means. I estimate my model, and then I plot my model. I'm sorry, I plot my observations here. With the observations right above them, using the text function R, I'll let you look at the details on your own, I actually plot the hat matrix diagonal values. Notice here's that 21st observation, the new one that I added. Look at its hat matrix diagonal value relative to the other ones. It is large. Not the largest, but it is large. And again, why is it large? Because the average GP in this data set is probably about right here, and its distance from that is large relative to the others. Then let's actually plot the models with and without that 21st observation. Without the 21st observation, we get our usual model that we've seen all the way back in Chapter 1. That's denoted by the dotted line. Now, with the 21st observation, look what happens. It exerts influence. It exerts leverage to that line by pulling it towards it. This is what we don't want to happen, because this now changes our understanding of our model. again, one of the most important things about a regression model is the slope, the B1 here. We use the B1 to understand the relationship between X and Y. And now our B1 is lower than what it was before. So essentially it's telling us in this particular case that there's maybe less of a relationship. Or, yeah, I guess you could say that. Because the two are measured on the same scale here. Anyway, so you can see the effect that this has. And we can look at some other examples too. So on the left side plot, I actually reduced the value of the high school GPA. Instead of being 4.35, it's 4. So that means that that observation is closer to the middle of all the high school GPAs. And as you would expect, the hat matrix diagonal value decreases from what it was before. But take a look at what happens then to our models. This is without, this is with that observation. Now this observation exerts less influence and doesn't cause that line to come as far down as it did before. Alternatively, suppose that we increase that high school GPA to 4.9. Now it's farther from the center of all the high school GPAs, and look at what happens to my regression model. It pulls it down even further than what it did in the first plot. So it exerts even more influence. It has a larger hat matrix diagonal value. Now if we go back to the original plot here, now notice that we have some observations that do have large hat matrix diagonal values, but notice that they're in the same general trend as what we had originally. And so because of that, they are not detrimental to the model's fit. They're not going to change it much. So just because you have a hat matrix diagonal value that's large doesn't mean it's bad. And to conclude this section then, let's take a look at the MBA GARD data set. So I just again pull out the hat matrix diagonal values with the hat values function. And then let's look at this criteria. How many of these, or which observations have a hat matrix diagonal value that's greater than 2 times p divided by n? We have a few. Let's do a plot to the hat matrix diagonal values. This is often done because, if you have a large number of observations, it's an easy way to look at all of them at the same time. So what I do is what's often referred to as an index plot. On the x-axis, I simply put the observation number. How did I do that? X equal 1 colon n. 1 to n. I plot that versus HII. Then I put in corresponding reference lines for us. Here's 2 times p divided by n. Here's 0.2, and I try to put a 0.5 in as well, and it's off the plot. And so we can see now where these larger hat matrix diagonal values are falling in terms of their observation numbers. Also, we see that if we use this other criteria, we don't have that many. Remember, we could go up to 0.5 there to have high influence. Okay. So, are there any questions? Okay, we'll stop there for now. And let's talk about the exam. So I will have virtual office hours in the chat room available from the course website. 9 to 10 p.m. on Monday night. So if you have any last-minute questions, please feel free to stop by and ask them. Like last time, the test will go from 11 a.m. to 12:25 p.m. So if you need an extra 10 minutes to finish the exam, you have it. You don't have to take it, but I'm making it available to you if you want. I don't make the test, I'm not purposely making the test longer either, since I'm giving you this extra time. It's just to help you out and you have this extra time. Remember the formula /R function help sheet. Again, it's available on the course website. Make sure you're familiar with what information is going to be given to you before the exam. I will pass this sheet out to you so you don't need to bring it in with you to the exam. The test covers chapters 4 through 9, excluding sections that we, of course, skipped. The actual test structure, there's 100 points possible. There's just 3 problems. The first problem, 62 points. There are 8 parts. You're going to get some data, and you're going to need to use R. So, just make sure you can just verify that you can do some stuff with R and that you can interpret the corresponding R results that you get. Problem number 2 is 38 points. There are 5 parts, and simply these are short answer questions where the parts are not necessarily connected in any way. So similar to the last exam, I think I had some short answer questions at the end. That's what these are like. You might have to write, a couple sentences, maybe 4 sentences to answer a particular question. And then lastly, problem number 3 is 3 points extra credit, dealing with something that we mentioned during class. So hopefully you weren't sleeping when we talked about it. So that's the structure of the test. It's going to be very similar to last time. And just to review, what I will do is I'll give you the paper copy of the exam, and that's where you need to write all your answers on. You use the computers that are in front of you as kind of like a nice calculator that does the statistical calculations for you. What you need to put on the test for an answer is the final numerical result that you get from using R on these computers. However, you need to go a step further. You need to actually show me how you found that answer. So actually, for example, give me the corresponding equation that you use, or that R used, to actually solve the particular problem. The reason why I want you to do that is because if you got the answer, the numerical answer wrong, and that's all you had, there's no way I can give you partial credit. Okay, so that's why I want you to do that. So there's a possibility that I can give you some partial credit. I have an idea of what you did and what you did wrong, and I can assign the partial credit. Now, if you have time, and only if you have time, please feel free to write a little bit of code on the exam. That again will help me give you partial credit if needed. But only do that if you have time. Code is not required. You can access TIN, RStudio, R, an internet browser that's pointed to my website or has the R help in it. But those are the only programs that you can have open on your computer, only software packages that you can have open on your computer. It is closed book, closed note, the test, but you have access to all my R programs available on the course website. So if you haven't done this already, it would be good for you to be familiar with my programs there so that you don't spend, let's say, 10 or 15 minutes looking through every single program to find a small bit of code. So if I ask you, for example, how to compute, or maybe I ask you to do Do I have an example here? Unfortunately, my examples in my head are from Chapter 10, and that's not good. Suppose I ask you to compute, let's say, SSR x1 given x2. And you have to think, okay, well, where did we do this before? Well, hopefully you remember, it was Chapter 7, so I should find the corresponding program in Chapter 7 where I did that before. Copy and paste in that code to your own program, make a small change to it, so put in the context of the data that you're analyzing, and there you go. You should not be spending many, many, many minutes looking through my R programs for help. You should have a general idea of where to find stuff. And just make sure, I said this, closed book, closed note. Please do not be communicating with anyone outside the class or inside the class via the computer. Okay, are there any questions about this, the structure of the tests and what's going to happen on Tuesday? Okay, let's review some of the material then. So, Chapter 4. It's a short chapter. Two main things that we talked about. We talked about the Bonferroni procedure. This is the first time we talked about it. And the purpose of the Bonferroni procedure is to take into account that, you are doing, in this case, it was multiple confidence intervals. Each of them at, let's say, a 95% confidence level. Then you might be wondering, well, what's the overall confidence level that I have that all these intervals are actually working, that they contain their corresponding parameters? And the Bonferroni procedure gives you a simple way to make sure that everything is okay, that it does work. Make sure you know how to do it, how to apply the Bonferroni procedure, but make sure also you understand how it comes about. Why do we just simply take, instead of alpha divided by 2, why do we do alpha divided by 2 times g? Why? Then the second thing that we talked about in Chapter 4 was something called inverse prediction. It's called inverse prediction because now instead of predicting y, we're interested in x. But let's say that we have a model that corresponds to using x to predict y. So we just kind of go backwards from that model. We come up with an x hat. Then we also looked at how to find a corresponding confidence interval with it. If you remember, unfortunately, there's not a nice little function r that automatically does it for us, so we had to actually program in the corresponding formula ourselves to do the confidence interval. So Chapter 5. This is when we first started talking about matrix algebra and matrix methods. There is nothing directly from section 5.1 to 5.6 because this is just background material. The basic of how do you multiply matrices together. Ideally, it would have been nice if we could have everyone have this material before they come into this class. But unfortunately, that's often not possible. So that's why we do this little review of what matrix algebra is. But starting then with section 5.8, you are responsible for the material. And this is where we start putting then our regression model into the context of matrices. Then foreshadowing then other sections, you should think about, well, why was this nice to be able to do? And why do we go through the trouble of doing this? Also, we talk about, for example, something called a covariance matrix, which, this might have been the first time that any of you have seen, that some of you have seen a covariance matrix before. Make sure you know what it is. How to find particular variances and covariances inside the matrix. And, of course, make sure that you understand something very simple, such as B is equal to x prime x inverse x prime y. Now, of course, you don't have to memorize those corresponding matrix formulas that we have there. That's all going to be on the formula sheet. but you need to know how to work with these equations, how to do the calculations in R. I once put on an exam a very, very small data set. I asked students to simply write out what x prime x inverse x prime y would be in terms of this particular data set. Actually write out the contents of the x and the y and so on. So just to give you an idea of something I've done in the past. Chapter 6. Now we get into multiple linear regression, where we have more than one predictor variable in our models. Using matrix methods, it's easy now to write out our model and write out other various calculations that are needed for multiple regression. One of the first things that we did was we looked at a two predictor variable situation with obviously one response variable, and we had a plot where it was kind of an abstract plot that helped demonstrate what a population regression model is and then what the sample regression model is trying to do. Make sure you're familiar with that plot. Similar to Chapter 1 where we had a plot for just simple linear regression. Now I could give you this plot now in the multiple regression context and ask you to label certain items on it. Of course, the matrix calculations, how to interpret the model. Now, one of the central things that we use to interpret then a regression model is we look at these B's, like B1, B2, B3. And if I want to understand then the relationship between X2 and the response, I would say something like, for every 1 unit increase in X2, I expect, or Y should, or I estimate that Y should increase by B2 units. But then you also have to add the following, since we're in multiple linear regression setting. Given all the other variables in the model remain constant. So remember, you have to add that part, but also make sure you understand why we need to add that part. Unfortunately, the R squared isn't always the best to look at in a multiple linear regression setting. Make sure you understand the problem with it. And then the solution, or one solution, is to look at the adjusted R squared. Remember, this adjusted R squared cannot necessarily be made to always go up as you add predictor variables to your model. Then we also spent some time looking at how can we examine if our model's assumptions are satisfied. So this is where we do various plots of the residuals, like a QQ plot, a plot of residuals versus y hat, for example, to examine non-constant error variance. All those big assumptions that our model has, we basically put the tools that we have from Chapter 3 now into the context of a multiple linear regression model, and so that we can examine our model. Make sure you're familiar with that. So it might be good to review the Chapter 3 material too, as well. Chapter 7, then the first thing that we started talking about was things called extra sums of squares, which involves stuff like this. SSR of x2 given x1. So given that x1 is in the model, what this measure looked at is given x1 is in the model, how has my SSE decreased? If it hasn't decreased much, then you might be saying, well, maybe x2 is not really worthwhile to have in the model, given that x1 is there already. If it decreases a lot, then it looks like, well, even with x1 in there, x2 is contributing something. It's being helpful to predict the response. We also introduced the concept of comparing a reduced to a complete model in terms of hypothesis tests. Make sure you're familiar with our terminology there. And then this led to then a partial F test. Make sure you can do a partial f-test. Also remember that a t-test and an overall f-test are just special cases of a partial f-test. Make sure you understand why they're just special cases. We also looked at the coefficient of partial determination, which is just directly connected to that partial, the extra sums of squares, that SSR x2 given x1, for example. Yeah, all this is looking at now the proportional reduction in SSE. And lastly, we focused on also multicollinearity. Spell multicollinearity. What is multicollinearity? Why is it bad when you have high multicollinearity problems? How can you detect when you have multicollinearity problems? And we had a nice little example where I simulated some data with two predictor variables that were very, very highly correlated, and we saw the problems that occurred when we included both in the model. Chapter 8. This is where we started talking about polynomial regression models. Make sure you understand what a first-order model is, what a second-order model is, what a third-order model would be, and so on. Remember how it's a little bit difficult, or the code to include, for example, a quadratic term is not necessarily intuitive in a formula argument for the LM function. We use the I function, where we say I parentheses x caret sine 2 in parentheses. That gives you a quadratic term. You can't just simply put x caret sine 2. Make sure you understand why. That was actually covered then a little bit later in Chapter 8. And we also talked about interactions. Well, what is an interaction? Well, it's when, the effects of let's say, x1 on the response are dependent upon the level of maybe x2. If that's the case, then you should have the x1 times x2 interaction in your model. Make sure you know how to do, for example, a hypothesis test to determine if an interaction is needed. And we also spent some time dealing with qualitative variables. So these are variables that are not measured on a quantitative scale, such as gender or political party affiliation. How can we include information from these qualitative variables into a regression model? And we looked at how to do that. Make sure you understand how to do interaction terms involving qualitative variables as well. Make sure you understand how R codes qualitative variables in the regression model as well, and how you can change the coding to fit your needs. And lastly, Chapter 9. This is where we start looking at how to choose between predictor variables. So we might have a particular setting where we have a lot of predictor variables, and we want to know which one should we include in one overall grand model. So we need to do what's called model building. In step 2 of the model building process, tells us some ways to choose between how to choose between particular predictor variables. Particular predictors. I have a hard time saying that for some reason. And ways that we talked about include R squared, adjusted R squared, CP, AIC, and then prefs. Obviously make sure you know what they are, why they work, and also how to interpret them. How do you choose between, let's say, two different models based upon these predictor variable selection criteria? And we also spent some time talking about forward selection, backward elimination, and forward stepwise. Make sure you can implement them, even without, let's say, the step function in R. Maybe I could give you some, without actually going to R, I could ask you a question that gives you, let's say, some AIC values or hypothesis test results, and ask you, okay, let's do forward selection. Which variable do we include in our model first? So I can have you step through it without necessarily you using R. So make sure that you're familiar with how to do these particular methods. Okay, that's all I have to say specifically about the exam. Do you guys have any questions? Either you're overwhelmed or you're like, this is going to be easy. I'm going to say it's going to be easy. That's what you're thinking. I hope so. I don't think it's going to be that bad, but with my tests, I do try to be comprehensive, and I try to make sure I'm grabbing. There's a lot of chapters here. I try to grab stuff from every chapter to make sure you can't just get off by saying, I'm going to skip chapter 4. That would be bad. Okay, so don't skip any chapters. I don't think it's going to be too bad. I wouldn't expect surprises. So. If you have any questions between now, yes.
Yes, can you talk a little bit about the conference collection?
What specifically do you?
Like in general.
Well, I mean, the idea of how to work with it is fairly easy. If I had, let's say, G different confidence intervals, then where the Bonferroni correction comes in is only with respect to your value from your t distribution. And so if you're finding confidence intervals, you would simply find, instead of the 1 minus alpha divided by 2 quantile, find the 1 minus alpha divided by 2 times g quantile. If you are doing hypothesis tests and you're working with p-values, find p-values the normal way, and then simply take g times that p-value. Okay? And that will be a Bonferroni corrected p-value. I think a good example of that is the last project where you had to do that. Does that help? Any other questions?
Can you give us an example of the short answer questions?
Oh, let's see. Maybe a longer one would be describe the difference between forward, backward, and stepwise selection. Okay, so you obviously have to write a few sentences. Tell me why. Tell me why a lower press statistic value corresponds to a better model. So we can write a few sentences. And I think, if I had a favorite part of the test that I write, I usually write tests in the same kind of format for all my classes. I always like these short answer questions because it helps me really narrow down onto specific topics to make sure that you understand them. I don't think my students usually feel the same way about the short answer questions, but I think that they're a good gauge of making sure that, yes, you indeed do know everything that you should know. Other questions? Yes?
The extra credit, will that be something germane to multiple regression, or could be any random, like I said, motorcycle?
Like I said, it has something to do with a particular thing that we mentioned during class. So the answer was not discussed during class, but the general topic was discussed during class. And if you would have done maybe a little bit of a search after class, you would have found the answer. Okay? I have a little bit of more room with extra credit. It doesn't necessarily need to be something that we exactly discuss through and through in class. And so what you could do is rewatch all my videos, and you'll find what it is, I bet. Other questions? Okay, that's it. Again, feel free to post a message to the listserv if you have any. Post a question to the listserv if you have any more questions between now and the exam. Also, of course, you can attend the virtual office hours too on Monday night. So that's it for today.